Today, we're not just going to talk about the mind, we're going to try to build one, sort of. We're diving into the world of computational modeling to figure out how our brains actually learn and why they sometimes get things so wonderfully and fascinatingly wrong.
So let's start with something we can all relate to. Superstition. You know, an athlete wears a specific pair of socks, which is kind of rare, right? Before a huge, totally unexpected win. And boom, suddenly those socks are a lucky charm. Our brains do this all the time, forging these powerful, sometimes totally illusory connections. But what is the actual mechanism at work there? Well, to find out, we have to go beyond just talking about the mind. We need to translate our ideas into what are called formal cognitive models, which is really just a fancy way of saying we're writing our theories as testable computer code. This forces us to be absolutely crystal clear about how we think learning actually works, step by logical step. Okay, so let's start with a really foundational idea, one you've probably felt yourself. We learn best when we're surprised by something. It's a pretty intuitive concept, right? But to make it truly powerful, we have to get really precise. And this slide really shows the key difference. On the left, you've got a verbal theory. People learn more when an outcome is surprising. It sounds good, sure, but it's super vague. On the right, though, we have a formal model, the delta rule. And all of a sudden, our idea becomes a machine. It takes an expectation, compares it to what really happened, and uses that difference to update its belief. This simple equation is basically the engine of a very powerful theory of learning.
The crucial part of that equation is something called prediction error. This is the absolute heart of a famous learning theory called the Rescorla-Wagner model. Think of it as the mathematical version of surprise. If you expect something to happen, and it does, your prediction error is 0. You don't learn anything new. But if the outcome is different, that gap, that error, is what drives change. It's literally the brain's signal to, hey, update your model of the world.
So we have this simple model built on the idea of surprise. But is it any good? I mean, can it predict something about how we learn that isn't totally obvious? Let's put it to the test. The model's first major triumph was explaining a really strange phenomenon called blocking, which shows that our learning isn't just about simple association. Let's see how our model handles it. So imagine this experiment in 3 parts. First, we teach our model that a light predicts food. It sees the light, it gets the food, it has a big prediction error, and it learns fast. Easy enough? In phase 2, we show the model the light and a new bell, followed by the same food. Then in phase 3, we ask the model, okay, what do you think of that bell all by itself? And this is where it gets so cool. The model learns absolutely nothing about the bell. Why? Because in that second phase, the light already perfectly predicted the food. The model's expectation was met, so the prediction error was 0. There was no surprise to drive any new learning. The light's prior knowledge literally blocked the model from learning about the bell. And this is exactly what happens in real experiments with both animals and humans. A huge win for our little model. Okay, so our model's looking pretty smart. It captured a really complex, non-obvious feature of learning. But now for the plot twist. What happens when we pit this perfectly rational machine against a situation where we humans are famously, well, irrational? We're going to test it with a classic cognitive bias, illusory correlation. This is where people form a really strong connection between two things, even when the actual data shows no such link exists. It's at the root of a lot of stereotypes and superstitions.
So here's the setup. You're observing behaviors from 2 groups, A and B. Group A is the majority and Group B is the minority. Now look closely. The actual rate of negative behaviors is identical for both groups, exactly 20%. Objectively speaking, there is 0 difference in the data.
So what does our perfectly rational model do when it sees this data? It nails it. The Rescorla-Wagner model correctly learns the true rate. Its final estimate for both Group A and Group B is 20%. It sees the world exactly as it is.
And here is the problem. The model is right, but humans are wrong. In this exact same task, people consistently overestimate the rate of negative behavior for the minority group. So our model's success is actually its failure. It's failing to capture the very bias we want to understand. It's just too perfect. Now this is where cognitive modeling gets really, really exciting, because the model's failure isn't a dead end. It's actually a clue. It tells us exactly what we need to add to make our model more, well, more human.
The big insight here is that the model isn't wrong, it's just incomplete. We can use it as a kind of laboratory to test different theories about why humans form this bias. We can literally write the glitch into the code.
So we have a couple of options here. On the left, we could just give the model a pre-existing bias to begin with. But a more powerful theory, over on the right, suggests the bias isn't about what we start with, but it's about how we learn. What if the learning rule itself actually changes for certain kinds of events? And this is the leading theory. The bias comes from our brain's sensitivity to distinctive events. Think about it. The minority group is rare, and the negative behaviors are also rare. So when those two rare things happen together, our brain essentially yells, "Pay attention to that," and it overweights that specific piece of evidence. So let's write that into our model. We'll temporarily boost its learning rate, but only when it sees a Group B member performing a negative action.
And look at the result. After this one tiny tweak to its learning rule, our model now sees the world just like a human does. It still correctly estimates the rate for the majority group at 20%, but its final belief for the minority group jumps all the way up to 34%. It forms an illusory correlation, just like people do, not because the data is biased, but because its learning process is.
So, we've built a model, we broke it, and then we fixed it to be more human. What's the big takeaway from all this? Well, for one, this whole approach forces us to be incredibly clear. Vague ideas like we overreact to rare events become a specific, testable line of code. It really lets us peek under the hood and look at the hidden rules that govern how we construct our own reality. And once we start to understand those rules, well, then we can start thinking about how to improve them. And that leaves us with a pretty big final question. By modeling the glitches in our own mental software, we've taken the first big step toward understanding them. So, if we can write the code that creates our biases, can we one day write the code that helps us debug them?